All right, screen share is set up. All right. All right. Great. All right, right on time. It is noon time. I will magnify, when I get to this. Okay, so don't worry. I did grade exam 2. Your grade should be in your grade book already. So if you find something suspicious, like, oh, I don't think this is my grade, I'll be more than happy to take a picture of your submission and then also give you my actual feedback. I actually took, relatively detailed notes on, why I gave you the grade that I did. So if you want to know that, that's fine. Just let me know. Yeah, so I found the distribution of the second exam to be quite different from the first exam. Some people who did not do so well in the first exam, just completely aced the second exam, and found a few other cases in the opposite direction too. So that was kind of surprising. I did not anticipate that. Quite a few people got relatively good score in the second exam. Even so, I took the 4th highest score of the entire class as the quote unquote 100%, and then we scale everybody accordingly. So some of you may see your score being more than a 4.0. Okay, so I think there are 3 people who got more than 4.0. Yeah, so that was that. All right, so any other questions before we start on the exam, the final exam from last semester? Nope. Okay, so we'll go ahead and get started. All right, so let me prep my side, okay, and magnify this so that we can see everything. So I can see. There we go. All right, we can have one more level because the margin does not really matter in this case. All right, so your instructions would be very similar to this. You have 2 hours. I have already put the final exam schedule on the calendar of this class in Canvas. So if you look at the calendar of this class in Canvas, you will see the actual date as well as time. I believe it is next Monday. So we are almost exactly 7 days away from the final exam of this class. The duration is 2 hours. Okay, so unless you have accommodation, your time will be exactly going from, I cannot remember the exact time. Okay, it's on the calendar itself. And the one thing I do recommend if you're going to use Canvas, again, either here or at a 4-year university, is to synchronize the schedule, with your mobile device. So I can actually see on my mobile device that the exam is scheduled at 12:45. Okay, so it's 12:45 on next Monday. That's going to be the final exam for this class. So that's, I think it's a really nice feature to be able to do it. So the questions have been randomized. Do not assume any one-to-one correspondence with exams from past semesters. In fact, just don't assume anything. That would be the best assumption. You can use any material that is printed or handwritten on paper prior to the exam. Same thing as the first and the second exam. Answers should have explanations of reasoning, and that should be basically step-by-step, logically link what a question asks to the concepts we introduced in class, my modules, lecture content, and consequently derive the answer. I also put in this section here, which can be handy for some people. So this way, it is a step-by-step process to look at the question and identify the properties of the word question then you can choose the correct distribution to apply to find the answer. So we'll get through this, when we get to the actual questions. You are allowed to use a calculator to compute the actual values. You need to write down both the expression being evaluated as well as the resulting numerical value, because I don't want people to just give me a numerical value without explaining where that is coming from. All right, so all questions carry the equal weight. That's going to be true as well for your final exam. So just as a reminder, it is good to double check, okay, to make sure that you know how many questions there are and not to miss one question accidentally or miss one entire page accidentally. All right, so now with that said, we can now move in and talk about the actual questions. I'm going to zoom out just by one little level here. So the first question, says TAC has 13 pairs of high key, because in Hong Kong you can buy these rejects in in the market, where they stitch the name of name brand products incorrectly. So the N turns into an H, so Nike becomes Hikey. So anyway, and you have to do this, because the A turns into another D. And also I think there's one extra D also in here. So basically I got different socks, okay? 13 pairs of one, 7 pairs of the other. And I put all the socks in the same drawer. For 3 days in a row, all the socks are washed, dried, mixed up and put into the drawers. For 3 days in a row after, so after all the socks are washed, dried, mixed up and put into the drawer, TAC has been randomly picking 2 socks out of the drawer each day. And I have been wearing mismatched socks every single day. So for 3 days in a row. You may assume TAC has a basic hygiene and put worn socks in the laundry basket at the end of each day, which means I'm not wearing the same pair of socks all 3 days. That is not the explanation of why they're all not matching. Okay, so altogether, 6 individual socks were picked, 2 at a time, and somehow I always end up picking not matching socks. All right, so the question is, what are the chances that this happens relative to just randomly picking 2 socks per day for 3 days? In your answer, be sure to explain your reasoning, formulate expressions, and carry out the calculations. Hint, treat each day as an experiment and find out the probability of each day, and then figure out how to combine the probabilities of each day into an overall probability of all 3 days. All right, so do we understand the question first? Okay, this is a word question. Yes.
So what you're actually doing is taking 2 socks out of the drawer.
Yes.
Wearing them and then putting them back into the laundry basket.
Yes.
What is the difference between that and the second line there? What are the chances happens relative to just randomly picking 2 socks?
It's just basically I'm just making it clear that I just want to know the probability of this happening. All right, so how do we approach this problem? So I think this is a good time to go back to what we saw earlier in the instructions, because we want to identify what type of distribution we are dealing with here. And then the hint is also really important, okay? The hint basically said for each day, you want to consider each day when I need to pick 2 socks out of the drawer as its own experiment, okay? So with only that hint, okay, in the last paragraph on its own, how many trials is in one experiment? Let's just take the first day as an example. Okay, so out of the 3 days, we're only focusing on the very first day. So the first day, I just reach out to my drawer. Okay, I took 2 socks out of the drawer. So if you look at that as an experiment, can we characterize that particular experiment? Let's first start with how many trials are we dealing with here and what each trial entails. So what do you think each trial entails in this experiment? Go ahead. Oh, okay. Grabbing a sock. Very good. Okay, so grabbing a sock is a trial. So the next question is, how many socks do I get to choose from? So we'll consider the first day, right? The very first day, the very first sock that I tried to pick out of the drawer. How many choices do I have? Okay, so this is where, many students actually miss this part, is I'm talking about 13 pairs. I don't have 13 of one type of sock and 7 of the other one. I have 13 pairs of one versus 7 pairs of the other. Okay, so I wasn't really trying to make this tricky by saying, pairs of socks instead of individual socks, because most people associate socks in pairs, right? So I wasn't even trying to be tricky. So now you look at this, okay, so let me use my, little stylus here. So we have, 13 times 2, which is 26 of the high keys. Right?
Yeah.
Okay, and then we have 7 times 2, which is 14 of the Adidas. Okay. So that means we have a total of 40 socks in my drawer, which is a lot. Question.
Would you consider being mismatched sock in one of the different each of the brand that mismatch?
Yeah.
Okay.
Yep. So mismatching simply means, two, one is from one brand and the other one is from the other brand. All right. So now, now that we know that each trial is picking one sock out of the drawer, the next question is, do we have replacement? In other words, do I put the same sock back into the drawer when I try to pick the second sock? No. So it is without replacement. Okay. So we go like, okay, so now we have identified that this is without replacement. Okay. Okay. All right, very good. And then the next question is, if it is without replacement, it's going to change the choices that I have for the second sock, right? How I choose the first sock will impact the chances of what I can pick as my second sock. Is that part okay? All right. So just from the first day, okay, looking from the perspective of the first day, so what are the chances that I would pick one, high key and one Adidas, sock, just on the first day? That's all I want to know. Yep.
26 or 30 for high keys, and
Mhm.
then 14 or 39 for Adidas.
Yep. So we have 1/26 as a chance, to pick. Wait, hold on a second. Let me rethink this.
26 or 40.
Okay, so it is, we got 26 of the Adidas, and it is out of 40. And then we have 14 of that's the high key. This is the Adidas, but then it is out of 39.
And this is this a matter if you pick up high key then Adidas?
That's a very good question. Okay. So the way I'm doing this calculation here, and I'm taking into consideration of the ordering. And if it is, in other words, am I looking at the chances of picking picking the first sock as a H type and then picking a sock as the D type as the second one, or the ordering is actually not important here, the way this is counted.
Ordering should matter, right?
So if the ordering is important, which means, which one am I wearing on my left, foot and which one am I wearing on my right foot? How would that look like in terms of the probability distribution? Well, socks do not, there are no left and right in socks, right? Most socks do not have left and right. So which one do I pick first as a H type and which one do I pick as a D type? So how is that taken into consideration here? If I just look at this number here, what is it representing?
This is the probability that you pick one high key and then one Adidas,
Yes.
out of all of the possible realities that there are.
Mm-hmm. So is that the number that we want?
No, we need to do it for Adidas first and then high key as well.
Right. So how do we fix that?
and we do the multiplication for that, which would be 14 over.
Are we
40.
multiplying or are we dividing? In other words, am I counting permutations or am I counting combinations?
Would you
We're
just-
counting,
You just do the other probability and then you add them together, right? Because it's
Yep.
out of the total.
okay, so we'll leave that question, kind of hanging for a moment, okay? So this is for day one. This is what happened on day one. So what is gonna happen on day two? On day two, how many socks do I have remaining in the entire drawer? 38 socks. That is correct. So of the 38 socks, there will be 25 of the X type. And then there will be 13 of the D type. Okay. Now, when you look at the denominator, 40 times 39 is correct. Because out of the 40 socks, 26 will be of the X type. But once I take one sock out, then there'll be only 39 socks left, of which 14 will be of the other type. Now, whether the 39 is associated with the 26 and the 40 is associated with the 14, does not matter. Okay, so this is for day two. And then on day three, I think you guys can kind of figure that part out already. We have 24 of the D type, and then we have 36 remaining in the drawer when I pick the first sock. When I pick the second sock, then we have 12 of the D type, and then we have 35 socks left. So now the question is, do we just multiply all of these things together to get our probability, or do we have to take into consideration the ordering of, which sock do we pick first? The ordering matters. So
Could you just multiply each of these values by 2 and then multiply them all together? And the reason I'm saying by 2 is because 14 over 40 times 26 over 39 is the same thing as.
they are.
So we just multiply it by 2 to take care of the ordering issue.
But the question is, do we need to multiply by 2? Do we need to divide by 2 for each day? Or do we need to do nothing on each day
No, I think we have to multiply each day by 2.
to account for picking different socks in a
Yeah.
different order? Don't think we need to do that.
I don't think we need to do any.
So I think if you just multiply, these three, so call this P1, P2, and P3, and you just multiply these three numbers, you get the final probability.
But that's only in this, doesn't that only take care of the specific scenario where you're picking high key first?
But you don't know. That's the thing, because when you pick the socks, you really don't know which one you're picking first. The only thing you care is that they're different. So when you reach in and you say, okay, I need one sock, and then I need another sock, right? So in that case, the chances of picking a Nike, a H-type sock first is 26 over 40. But once that is taken out, then the chances of picking up a D-type sock is 14 out of 39 on the first day. But you're basically saying, but what if we pick a D-type sock first? So that would be a 14 divided by 40 times, the 26 divided by a 39. That's the second one.
So the way I'm seeing it is like, if there's a bunch of universes laid out before me, whatever this number comes to, let's just say like 10,000. There's 10,000 different ways that I can pick socks, right? Then going through, I would want to add up all the ways I can pick high key first, all of the ways I could pick the Adidas first, and then like all of the high key first, and then 2 Adidas, et cetera, through the different ways that I can pick the socks.
There, like if you had it open for you, so like if you pick it first, then you probably, but then you got bring up one of the Asians, say, and I probably choosing one of
Okay, so let's flip this around and look at it from a very extreme perspective, because that's usually how reasoning will also work, is to push it to the extreme. So what if I have none of the D type song? Everything is the H type. Okay, so if everything is the H type, then we have zero probability to pick the other one, or we can just say well, there's only one of the other one. Okay, because what I want to do is to push it to the extreme, so that whether you need to multiply by 2, whether you need to divide it by 2, it becomes more obvious, of whether that needs to be done or not. In other words, the other way to look at this, okay, one more way to look at this is I did not specify anything about, did I wear an H type sock on the left and a D type sock, on the right. So the ordering does not matter, right? So that part is obvious. Ordering does not matter. So it would be the same thing as you have a bag of a bunch of socks, and you're trying to pick 2, and then you want the 2 socks to belong to 2 different groups instead of the same group. Doesn't that remind you of the lotto ticket thing? You go like, what does it have anything to do with the lotto ticket thing? Because the lotto ticket thing has 5 numbers, right? But remember, we had to deal with the problem of what if we want 2 matching and then 3 not matching? So we have to pick, the number of the non-matching and the ones that are matching. So do you remember how we did that calculation? Okay, so let's try to remember that. Okay, so we'll get back to this one. It is the same thing. Yeah. But I want to make it clear that how this is relating to a problem that we have solved already. Okay, so we got 5 numbers on the lotto tickets. There are 5 numbers on the lotto ticket. And let's say these are the matching ones and these are non-matching ones. And I want to find out, how many tickets are like this out of the total number of tickets. Is that okay? Because I want to find out the Powerball number is not being considered in this case. Okay. Okay. So do you guys remember how we computed the probability or how we do the counting in this case?
Out of 63 numbers.
So we have 69 numbers to choose from, right? So out of the 69 numbers, 5 are the lucky numbers. So we want 5 choose 3 of the lucky numbers. And out of the 69 numbers, 69 minus 5, which is 64, are the non-lucky numbers. Of those, we need to choose 2. You remember that? Okay. So that is how we figure out the number of ways to pick out 3 out of 5 of the lucky numbers, 2 out of 64 of the non-matching numbers in order to make the ticket. So now, if you translate that problem to what we're trying to solve here, what does it become? Well, let's take a look. Because we're just choosing 1. Okay, so we have 26 choose 1 and 14 choose 1. So now we have 26 choose 1 times, what's the other one? 14, I think. Choose 1. But that is going to give you the number of ways, but it's not going to give you the probability. So how do we do the probability thing? You have to divide it by the cardinality of omega, which is the set of all the possible outcomes. So do you remember how we did with the lotto ticket? If I ignore the Powerball number completely, okay, how many tickets do I get? When I have 69 possible numbers and I need to pick 5 out of those. I mean, the way I said it just answered the question, but I want you guys to kind of relate them. We have 69 numbers in the basket, and somebody just need to reach in and pick 5 of those numbers, and the ordering is not important.
69 choose 5.
69 choose 5, exactly. So we have 69 choose 5 in this case, but in this case, what are we looking at? How do we get the 69? That's the total number of numbers, right? Of which 5 belong to one group, 64 belong to the other group. So in our case, what would be the total number of socks?
40.
40. And out of 40, how many are we choosing? 2. Yep. So that is the actual calculation, and this is where, the 2 comes into play. Because, you have 40 choose 2, so that means, this whole thing becomes, 40 factorial divided by 38, 38 factorial. Oh, my palm is causing a little bit of a problem here. Oh, no, it's a Zoom. I have to move the Zoom. You guys cannot see it, but it's causing a problem on my side. So 39 factorial, and there's a 2 factorial here. So you have to take that into consideration. Are we good so far? So whatever this number is, okay, whatever this number is for day 1. Is that okay? Yep.
You're multiplying the bottom number by 40 over 38 factorial.
Say it one more time.
So are you multiplying the bottom number by 40 over 38 factorial?
The bottom number, you mean this part here?
That's what it was.
That's
Yeah.
40 choose 2. So what this means is the number that we have here, that is not correct. It is missing a, yep, the denominator is missing a 2, times 2. So that means, okay, go back here. This thing here is 38 factor, is, okay. So you have these 2 cancel out, you end up with 40 times 39. So we still have a 2 factorial, but the 2 factorial is the denominator of the denominator, which means if you want to move it up, that's possible too. So that means we really need a multiply by 2 for each one of these. But that's why we need to do a multiply by 2. So there's a way to explain that by mapping this problem to the one that we have solved already in class. So that is the whole thing about how to look at these problems is, can you relate it to something that we have solved already? Is that okay or not? Are there any questions about this explanation? That's for one day, yes. Because you have 26 choose 1 times 14 choose 1 divided by 40 choose 2, right? That was the conclusion based on how we mapped the SOC problem into the lotto problem. So when you look at this, 26 choose 1 is what? How many ways can you choose one item out of 26 items? 26, right? All right, so we got a 26, which is what we got here. Same thing with the 14, no problem here, because choosing 1 is easy. So now the question is, what is 40 choose 2? So when you expand 40 choose 2, okay, 40 choose 2 is 40 factorial divided by 40 minus 2, the whole thing factorial, times 2 factorial. How do we know that? That is, how do we get from 40 choose 2 to 40 factorial divided by 40 minus 2 factorial times 2 factorial? Where is that coming from?
Definition.
It's exactly, it is the definition of the computation of combination, the number of combination. So now when you look at this is 40 factorial, this is 38 factorial. Because of the accordion effect of factorial, this boils down, okay? When you cancel these 2, it becomes 40 times 39. Is that okay? 40 factorial divided by 38 factorial is 40 times 39. Is that okay? All right, but we still have this 2 factorial, which is just 2 unaccounted for. But this 2 factorial is the denominator of this thing here, and this entire thing is the denominator of this thing. So that means we can just take this out and stash it over here. It would give us the same value. That part is algebra. Is that okay? Maybe? Because when you divide the denominator itself by 2, then the entire fraction is multiplied by 2. Are we good so far? Yep.
So why wouldn't we use binomial theorem in this case, binomial distribution?
Very interesting question. We do not use binomial distribution in this case because the chances actually changes depending on, I mean, once you have choose one, choosing one is not going to change it, but it's going to change the distribution on the second day. It's also going to change the distribution on the third day. Now, a interesting generalization of this problem is to pretend that you are not a human with only 2 feet. Instead, you are let's make it more interesting. I was about to say octopus, which only has 8 limbs. We'll make it even more interesting. Let's say you're a heptapod, which means you have 7 limbs. And each day you have to choose 7 socks. And I want 4 matching, 4 of the H type and 3 of the D type. How would you generalize the solution that we have now to handle that? So that's just that is just one way for me to push the reasoning that we have done so far, because it really is the same reasoning. All you're doing is you're changing out of the first type of socks, how many are we choosing? Out of the second type, how many are we choosing? And out of the total, how many do we need to choose? Those are all the only things that you have to change, even though it sounds like a much more difficult problem because now you have 7 socks to choose each day, but the same method still applies. Are we okay with this one? But that's only for the first day. What about the second day? Actually, it's pretty easy because we start with 25 of the H-type sock. We start with 13 of the D-type sock. We only have 38 socks left, but of which we're only choosing 2. So that would be the probability of choosing mismatched socks on the second day. And then on the third day, it's going to be 24, choose 1. Oops, wrong symbols. 24, choose 1, times 12, choose 1, divided by 36, choose 2. That's on the third day. This is for the third day. This is for the second day. And this is for the first day. Multiply all 3, and then you have the answer. Why are we multiplying the 3 and not adding the 3? Because of the tree thing. If you look at this as a tree thing, you basically say, okay, on the first day, how many ways can I choose this mismatched socks, right? And in each node corresponding to how I chose the 2 socks on day 1 becomes the starting point of the second day. So that's why we are multiplying, because the probability of landing on one single node after the first day is becoming the starting point of the second day. So when you look at it that way, then the last day or 3 days, you're looking at a 3-level tree, and the 3 events are happening in sequence, they're happening in the sequence, and that's why you're multiplying those probabilities. Is that okay? Are we kind of visualizing how the days, how the possibilities are kind of looking as a graph? Maybe. It's kind of hard to draw that graph because choosing 2 socks out of 40 is a really, really big fan out. How big of a fan out is that? If I just want to look at, if I want to visualize and look at all the number of ways of choosing 2 socks out of 40, regardless of the type, what is the fan out of that particular tree? It's a single level tree, but what is the fan out? 40 choose 2. How big is 40 choose 2? It's a pretty big number. We just did the calculation over here. It is 40 times 39 divided by 2. So we are looking at 20 times 39 divided by 2. This is 10 times 39, which is 390. So that's why I'm not gonna draw that graph or tree, because it's gigantic. Is that okay so far? So we can come back and look at this, if you guys have any questions. And then meanwhile, we're gonna move on to another question. Say again? The final answer? So the final answer would be the product of these three. So if you have a calculator, that should be pretty easy to calculate. If you don't have a calculator, it is still relatively easy to calculate. Are you guys doing the calculation right now? I need a dumb terminal. Where's my dumb terminal? I need a. Okay. Okay, this is my dumb terminal. So with 25 times 14 times 25 times 13 for the second day times 24 times 12 on the third day. And then we need to divide it by, then we have to multiply by 2 by 2 by 2. That's the entire numerator. And then the denominator is going to be 40 times 39 for the first day. And then it's going to be 38 times 38 times 37 for the second day.
36.
And then 36 times 35 on the third day. Oh, syntax error because I forgot to close paren. There you go. Is that what you guys are getting? Okay. So 0.9862 or roughly 9.8% or 9.9% is the chances that I wear match socks on all 3 days in a row.
Pretty slim. Pretty slim.
Well, 10% is not slim, but it's slim, a little slim. All right. So are we doing okay so far with this one? Okay, the most crucial part is how do I map this problem to the lotto problem? That is the most important part, is that particular map.
So what was the logic for multiplying by 2? I don't understood the mechanical part of connecting to the logic. But if you don't go that route and you just understand it logically, why would you? If you want to do this problem intuitively, just like 20.
Because you guys cannot see it. I forgot to. Because this is only taking into consideration of choosing a H type, then a D type. And then there's the other chance of picking a D type and then an H type. That's why there's the ×2.
Okay.
Because for the same combination, there are multiple permutations. But the permutations, the ordering is not important to us. But when you're actually picking out those socks, permutation is what naturally comes out.
Should you also think of it as like the 26/40 times the 14/39 plus 14/40 times 25.
Yes, same thing. Yep. Yep, because you have two alternatives.
Yeah.
In that case, you have the alternatives. Yep.
So in case we had to choose 3 socks instead of 2, would you have to multiply by 3 or by the factorial of 3?
The factorial. Because of 3 things, let's say we have A, B, and C. Now, whether those A, B, and C, whether they are belonging to the same classification or 2 different classification or all 3 different classification is not important because those are still 3 unique socks, right? So you have 6 ways to arrange 3 things, in terms of permutation, because you have ABC, ACB, BAC, BCA, CAB, and then CBA. And that's why there are 6 permutations when you have 3 items. And that's basically what the 2 is representing, is 2 factorial. So in this case, from the intuitive perspective, we kind of go like, oh, so it's just a matter of which one do we pick first, which is intuitively easy to understand, but it's harder to extend when you say, what about 3 socks? What about 4 socks? So by looking at it from the perspective of permutation, then it becomes much more extendable to multiple socks, which is also what the original Lotto problem deals with. Because the original Lotto problem that we had is only going like, oh, okay, this 5 is representing the 5 factorial. So that's why, I said it's important to map that question all the way back to the Lotto problem that we have solved already, that I have explained in class already. Is that okay? All right. So if anyone is curious, you can actually type copy and paste this question into Chat GPT and see how it solved the problem. You did try it? It did not solve the problem? Maybe not with this one. Some of the other questions it was able to solve here really kind of perfectly. All right, so we'll move on to the second question. So the second question is, you are given a trace running the A-star algorithm. The initialization is not included in the trace. As much as possible, reconstruct the original graph via the vectors, the vertices, and also the edges, the edge distance function, and the heuristic function. The destination vertex is known to be V5, sorry. All right, so be sure to explain alongside the trace how you determine the elements of the set. Answer without explanations will not receive any points, blah, 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 blah. And you can also draw a graphical graph on paper and so on and so forth. All right, so let me just kind of skip to the trace itself. This is the trace, okay? So the way the trace works is it shows you that O, the set O, starts with element V1, and then we choose V1 as variable C, and then O becomes empty because we have to remove whatever chosen vertex from the set O, and then we explore the outgoing neighbors in this case. So N is guaranteed to be an outgoing neighbor. V3 is an outgoing neighbor of V1. And then we compute T based on the G value of V1 plus the distance between V1 and V3 as an edge. And T turns out to be 2. And that turns out to be less than the G value of V3. And so we do all of these updates. So the question is, based on this trace that looks like this, indentation reflects the level of the statement in the original algorithm. Based on this trace, how much can you reconstruct the original graph along with the distance function and the heuristic function? That is what you need to do. All right, so when you look at this, you go like, but Ted, you have never illustrated this kind of problem before. Well, that is true, but we did talk about the A-star algorithm, okay? And there's a homework assignment on the A-star algorithm. So this actually can be helpful to do your homework, the A-star algorithm. Okay, so what do you need to solve this problem? That's the first thing, okay? So what are the things that I need? What are the tools that I need to solve this problem? You have a bicycle that is broken, okay? What do you need to fix the bicycle? Depends on what is broken about it, right? So in this case, I think having the basic diagram to draw, how a bicycle is put together can be useful. What would be the equivalence of that in this class, in this particular question? The A-star algorithm itself. Okay, second thing. Like, well, assuming, since this is the entire trace, there are no unknown steps or hidden steps from before. So if I just look at this part here, is that telling me anything significant? That O as a set starts with a single vertex of V1. What is the significance of that? How do we initialize O as a set with the A-star algorithm? Yes. It's the origin. Okay. So now we know V1 is the origin. Okay. So the next question is, can we have multiple origins with the A-star algorithm? Nope, there's only one. Okay. So that means I don't have to worry about some other vertices being the origin. But what is the significance of the origin in terms of the initialization of the three things that we have to track for every single vertex? There's the pref, which is the previous of something. And I think with that one, all vertices are initialized with unknown. Okay, so all the previous are unknown to begin with. Okay, so the origin is not special in any way. What about the G function and the F function? The G function, what does it track? What is the meaning of the G value of a vertex? Well, okay, it is initialized to 0, but why? Because we want to understand why G of the origin is initialized to 0, because that will help you answer the questions along when we look at the trace. The G value is
The G value is just the shortest path to the vertex
to that particular vertex, right? From
from the origin.
From the origin, very good. So if I'm asking what is G of V1, what do you think it is supposed to be initialized to? It is 0. Because we are asking what is the length of the shortest path from the origin to itself. You basically go like, I'm already on it. Okay, I don't have to go anywhere. So the length of the shortest path from the origin to the origin is 0. That is part of the initialization, but every other vertex has a G value of infinity, right? So if I just kind of scan through this whole thing here, do you think I can at least get a sense of what other vertices are in this graph? And how would I do that? How would I know what are the vertices, what are the other vertices of the same graph? Tracing C and also O, right? I mean, every vertex that we discover will eventually be an element of O, and then will be taken off, and the new things will be explored, and it will stash into O again. And also the outgoing neighbors, right? The N. Okay, so we'll identify what vertices are in this particular graph. So I'm going to pick a different color here. This is our origin. It is definitely a vertex. V3 is one of its two, it has two outgoing neighbors, right? It has V3 and V7 as outgoing neighbors from V1. How do we know that? How can I just look at N equals to V3 and go like, oh, okay, N3 is V3 is a outgoing neighbor of V1. How do we know that? How does N appear in the algorithm? For each outgoing neighbor and blah, 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 right? So that basically puts a constraint of what N can be bound to. They all have to be outgoing, they all have to be outgoing neighbors of V1. In other words, not only do we know at this point that V1, V3, and V7 are vertices, we also know how they are connected. So now we know, okay, so I'm just going to pick up here. V1 goes to V3, and it's also V7. I have the edges. Okay, but you're supposed to also know about the D function of the edges. Okay, in other words, what is the distance between two vertices on a single edge? Can we infer that from here? Yes, okay. So that has to do with which particular variable? T. T, very good. So T, how is T defined? T is G of whatever C is, plus the distance function from C to N. Okay, but Tech, we never know anything about G of V1. Well, we do, because V1 is the origin. And as the only origin, it is the only vertex that starts with a G value of 0. Very good. So if G of V1 plus D of V1, V3 is 2, what do you think is the distance of the edge V1 to V3? 2, exactly. So now we know this is 2, and then the other one is going to be 3. Cool. Oh, but Tech, you also mentioned something about what is the difference between the G function and the F function? Because, oh, look at this, they are different, but these two are the same. What is the F function with respect to the G function?
That's the heuristic, right?
f of something is the same as the g of something plus the heuristic function of that something to the destination. Okay, so if I know this, can I know something about the heuristic value between V3 and the destination vertex, whatever that is? It's going to be 13 minus 2, which is 11. And then the other one from vertex B7 to the destination vertex is going to be a 0 because G and F are the same. Okay, that looks kind of dubious because we don't even know what is the destination. So let me check whether the question said anything about the destination vertex. Yeah, so the question says it's V5. So now we actually know that it is V5 being the destination. There we go. In other words, this is what I want you to do with a question like this, is look at a trace, look at the algorithm, and then find out what you can infer from the trace and also the algorithm and reverse the whole process and get back to, oh, so we have these edges and then we have these vertices and then the distance function is like this between these two vertices and then the heuristic function is like this between this vertex and the destination vertex. Are we doing okay so far with this? Now it does get a little bit complicated later, but the process is not any more complicated. It's just that you just have to keep tracking things. All right, so let's take a look at these two here. So we got V3 and V7 here. We chose V7 because the F value of V7 is lower. And then we remove V7 from O. And then we use V2 as a neighbor of C V7 here. So right here, okay, because of this and this, I now know there's an edge going from V7 to V2. Does that make sense? Yes. Okay. But how can I compute the distance function, from V7 to V2 based on T is 9 at this point? Exactly. So this 9 is basically, so 9 minus 3, which is the distance from V1 to V7, has to be the distance of the edge from V7 to V2. So that's going to be a 6. So this is going to be a 6 here. Are we still doing okay so far, or do we have any questions? Mm-hmm.
So 9 is the distance from the origin.
Say again?
9 is the distance from the origin.
9 is the distance from the origin. That is correct. Yep. Based on the length of the shortest path currently discovered. Yep. All right. So between 9 and 12 here, between these two, what kind of information am I getting? What is the difference between the F function of a vertex and the G function of exactly the same vertex? The heuristic, exactly. So in this case, we now know that the heuristic function of V2 to V5 is 12 minus 9, which is a 3. So now we know H of V2, V5 is 2. Is that okay so far? So if you're not familiar with the A-star algorithm, what I'm saying right now may be going like this, okay? Because if you're not familiar with the algorithm and you're not looking at it right in front of you, it becomes difficult to track what variable is doing what in the algorithm. So that means, what is that telling you about the preparation for the final exam? Definitely want to include a printout of the algorithm, or if you're like me, you have it memorized already, then you can just use your memory. I would print it out, okay? If I were taking my own test, I would still print out my own notes, just so that I can have it with me, okay? Having scratch paper would also be helpful, because this way you can actually draw the diagram and actually run through scenarios on paper at the same time. All right. So what else do we know? Okay, so can we identify from the next iteration of the loop what kind of information we can glean out of this. We know there's an edge from V2 to V9. Because between C and N, there's an edge. Okay, so we just draw an edge between V2 and V9. So here is V2 and V9 is not drawn yet. So I'm going to just draw V9 over here. Do we know the distance between V2 to V9? We know T is 17. In other words, there's only one single path here, so we don't have to worry about which path we are talking about. So we have 17 minus 3 minus 6, which is what? An 8, I think. Okay, let me double check. Yep. So that has to be an 8. And now we have to look at how we update the F value. It is, the G value is 17, the F value is 20. So that means the heuristic between V9 and the destination is 3. So H of V9 to V3 of V5 is 3. Yep. V5, they're all the heuristic function, the only heuristic function value that we care is from a vertex to the destination vertex. So if V3 is not a destination, we really don't care. The idea is, yeah, go ahead.
I think he means for the previous one, the V2 to V5.
From V2 to V5. You mean this one?
Yeah.
That would be a 3, that is correct. That would be a 3 because the F value, the difference between the F value and the G value is 3. So I just wrote down the incorrect number. Are we doing okay so far? Is this getting kind of mechanical at this point? Okay. But this is still based on the understanding of the algorithm. So the test, the exam, the questions are really here to see if you understand the algorithm. Should we finish this entire thing or should we move on? Move on, okay? I can give you the key, I can give you the answer, I mean, that's not a problem. Yep.
That would be nice.
Yep.
Yeah, because I discovered some bidirectional arrows with different distances. I don't know if that was doing for it.
Okay, yeah, I can give you the answer, the key.
Is this the only final exam that's posted or?
This is the only final exam that's posted. All right, so for question number 3, I'm just looking at the time here. We still got 20 minutes, so I'm hoping to touch on every single one, but I think this one we actually worked with already. It is one of the announcements. Do you guys remember?
Yeah.
Yep.
Oh, yeah.
Okay. I think with this one, the ChatGPT can actually find the correct answer with all the steps. So, but do you guys want me to talk about it again or not?
Can you just talk about the first part? I think it requires 2 sigmas and there's a trick in there. Can you just cover this, just explain that?
Yeah, sure.
Just to add on.
Okay, so let me start from the beginning. The grower has 40 spots to grow a crop at the beginning of the growing season. So you've got 40 slots, okay? Unfortunately, the seed stock, no, this one we have not talked about because this one has tempering. Okay, so the tempering is the part that makes this one a little bit different from the one in the announcement. The one in the announcement does not have a saboteur trying to sabotage the operation. This one does. Okay, so let's read the question. So we got 40 spots, okay, to grow a crop at the beginning of the growing season. So all you need to do is to imagine you have 40 empty pots and say by the starting point of the growing season, I want every single pot to have a seedling in the pot so I can actually get some money out of the plants. Out of the entire 115 seeds in stock, so this is just looking at the stocks, 6 are sterile and guaranteed not to germinate. So somebody intentionally put in 6 sterile seeds in the stock, to kind of mess up the whole thing. The other 109 seeds will germinate with a chance of 0.9. So are we understanding the problem right now? Okay. Out of the 115 seeds that you can choose from, 6 guaranteed not to germinate, or you can look at it as a germination rate of 0. Okay. The other 109 are germinating with a success rate of 0.8. The grower cannot distinguish a normal seed from a clone. So when you look at the little jar of seeds to begin with, you look at those 116 seeds, 115 seeds, they all look the same to you. Okay. So the grower now guesstimate that a buffer of 17 seeds should be enough. So that means the grower out of the jar will pick 57 seeds to say, okay, I will try to germinate these 57 seeds. Out of the 115 in the jar, hoping that at least 40 will be available for the growing season. So out of the 57 seeds that we pick out of the jar, we are hoping the 40 will germinate. Are we good? Are we okay so far with the question? Okay. So you are hired as a consultant to help the grower to optimize the number of seeds to germinate. Compute the probability that the grower will indeed have at least 40 seedlings. So that's the question. It is almost the same as the one that we dealt with earlier in the announcement, but this time we have a little saboteur, putting in sterile seeds into the jar of seeds. So how is that going to mess up the original calculation here? And what kind of distribution are we looking at? Okay, so now you have to, again, look at this from the perspective of experiments. Okay, so when you look at this as an experiment, what is one trial? And what is the property of a trial? So I want you to imagine that you have two kinds of marbles, okay? You have red marbles and you have blue marbles. The red marbles represent the sterile seeds. The blue marbles represent the normal seeds, okay? Except you cannot see it, okay? They're all mixed up in a jar. So you have a jar of 115 marbles, of which 6 are red and 109 are blue. Is that okay? So the first question is, if you are to choose 57 marbles out of this collection, what are the chances of getting, you can get at the most 6 of the red ones, right? So let's take a look at those particular possibilities. You need to pick 57 seeds, okay? So you need to pick 57. So out of the 57, you can have 51 of the blue, 6 of the red. Is that correct? You can also have 52 of the blue, 5 of the red. 53 of the blue, 4 of the red, and so on. All the way down to, you have everything of the blue, which is 57 blue, and 0 of the red. Does that make sense? That there are these possibilities. How many possibilities are we looking at here? Not 6, because we counted from 0. So if you count from 0, it counts up to 6. There are 7 of these branches. Okay, so now you have to look at each branch and go, okay, let's pick one of these branches and then compute the actual probability of having at least 40 seeds that can grow. Okay, so let me pause here, because once we get down to one particular distribution, the rest is kind of the same as what we had before. But let me first get back to how we end up with these things. I'm just kind of I'm attempting to. Okay, fine. We'll do it this way. Sigma I equal to 0 to 6, and then we have some kind of fancy function f, and the fancy function f is going to say we're going to pick 51 plus I as one parameter, and then I as the 6 minus I as the other parameter. Okay. So what f is representing is the chances of, picking 51 blue, 6 red, and then 52 blue, 5 red, and so on. So this will account for all the 7 chances, the 7 possibilities. I'm gonna add up all these 7. Are we doing okay so far with this? So the next step is to figure out what is f, the function f. But are we looking at this sigma notation and understand what each item in the sigma is representing? You good? Okay? Okay, so what is I representing? Sorry? That and also the number of red marbles. Okay, the ones that do not germinate. Okay, all right. So now the question is, okay, so now we simplify the whole thing and we just look at f of, okay, 51 plus I would be the blues, okay? And then 6 minus I would be the reds. So what is that? That is the probability, okay? So I'm looking at this and we want this to be the probability of getting at least 40 seedlings. Okay, but can we, how do we calculate that? Remember what is B representing? B is representing the normal seeds, which has a germination rate of 0.8. And then the R is representing the sterile seed, which has a germination rate of 0. Why do I even need to know R? I don't know. I don't. Okay. Do you see what I mean here? Because only the blue marbles representing the seeds that can actually germinate would contribute anything to the 40 seedlings that I actually need. Right? Okay. So at this point, okay, so the first problem is the same thing as the lotto problem. Okay. So the lotto problem here, which is, there's one little thing that I forgot to mention here. There's also the choosing problem, because now you have to remember, out of 57, we are choosing I. That has to be associated with this probability. Okay, think about it this way. I am I made a mistake here. So let me take that out. Okay. Okay, so let's focus on this one first and then we get back to the other one. So if I know that we have this many germinating seeds and this many dead seeds, how do we figure out the probability of getting at least 40 seedlings? What kind of distribution are we looking at? What kind of experiment are we looking at here? So can we translate this part here into an type of experiment that we already talked about? Binary, okay, binomial distribution. Okay, it is a binomial distribution because we look at this as an experiment with B primes. Yep. It's more different. It's more than just that. But we'll focus on this one first, and then we go back to look at the coefficient with the function f. So with f of BR, we already know that we are only talking about B of the seeds that can germinate and R of the seeds that cannot germinate. So R for the most part is useless in this case because it's not going to contribute to the 40 seedlings that I actually do need. So someone mentioned this is a binomial distribution, and that is correct. So if this is a binomial distribution, what is one single trial of the experiment? Look at one seed and see whether it germinates or not. That is one trial. Okay, so it has a 0.8 chance of germinating and a 0.2 chance of not germinating. But whether one seed germinates or not is not going to limit whether the next seed is germinating or not. So that's why it is a binomial distribution. So how do we figure out the probability of having at least 40 seeds germinating out of B? It's a binomial distribution. So what is the general format of a binomial distribution? The general format of a binomial distribution is by itself a sigma notation, right? And we have index I going from something, going to something. And then we have something here, choose something here. And in this case, we have the germination rate of 0.8 to the power of something. And then we have the non-germinating rate of 0.2 to the power of something. So the question is, what do I use to fill in these boxes? Okay, so remember, we need at least 40, right? So 40 has to be here somewhere. So where do you think 40 is going to go? We need at least 40. So that means 40 is going to be some kind of a lower bound. Yep. So we are looking at least 40 germinating. What about B, which is representing the total number of seeds that can germinate? So we're looking at the off chance of, well, maybe we can even consider that every single one is germinating. So we have more seedlings than we actually do. Is that okay so far? All right. So what about how many are we choosing from, and how many are we choosing out of that many? We are choosing the number of seeds that we want to germinate out of the total number of seeds that can germinate. So how many seeds can indeed germinate in this case? No. No. Look at the parameters. B. It's 51, for the first I equal to 0 over here, but it is B here.
Yeah.
So out of B seeds that can germinate, we are now calculating of those many, we just want I, and I changes over time, with each iteration, we just want I of them to actually germinate, but it has to be at least 40. Okay, what do you think goes here? 0.8 to the power of. That part is just a pattern of a binomial distribution, because when you look at a binomial distribution, how B and I relate will answer the question of what goes into these two boxes here. Okay, so I want I many of those to germinate. So what do you think 0.8 should be raised to the power of? I. Okay, this is the number of seeds that we want to germinate. So that means whatever 0.2 is raised to the power of, that exponent is representing out of B many, this many is not going to germinate. So what would that number be? B minus I, very good. Okay, so we got B minus I. All right, so now that we have figured out what is B of F of BR, the next question is now getting back to the original question, do we have a multiplier over here? In other words, we are in this case looking at 51 plus I of the germinating seeds, and then 6 minus I of the non-germinating seeds. Wait, that sounds a little bit like the Lotto problem. Remember the Lotto problem? We have 5 numbers. And of the 5 numbers, sometimes we say, let's look at the number of tickets where 3 of those 5 numbers are matching and 2 of those numbers are not matching. Remember that? Well, it is the same thing over here. So when we look at this, then we have to look at the probability of getting 51 plus I of the germinating ones and getting 6 minus I of the non-germinating ones out of how many? Out of the 57. So we are now looking at the probability here by itself, where you have 57, you have 51 plus I. No, okay. Oh, I see.
So
out of the total. Yeah, go ahead.
50. So it be 6, choose 1, multiplied by 51. Sorry.
Okay, so let's try to map this back to the lotto problem, okay? So in the lotto problem, we have 5 numbers. In this case, we have 57 numbers. We have 57 things. And then with the other problem, we have the winning numbers and the non-winning numbers. In this case, we have the seeds that can germinate and then the seeds that cannot germinate. And then we have, in the original problem, we have 69 to choose. And then this time we have 115 to choose from. So we know this is going to be divided by 115, choosing 57 out of those. Because this number here, 115 choose 57, is looking at, if I were to look at the entire jar of 115 seeds, how many ways can I choose 57 seeds out of those 115? That is representing omega, the total outcome of the total number of outcomes here by choosing that many. So now, when we out of the 57, we have to divide it into 2 groups. One group are the ones that can germinate, and the other one will be the ones that cannot germinate. So we are looking at, I'm trying to map this back to the lotto problem. So the lotto problem is looking at the winning numbers versus the non-winning numbers. So now we have to look at the seeds that cannot germinate, and how many cannot germinate? Nope. The Salvatore put in more than 6 non-germinating seeds into the whole thing. What was it, 6? It was 6? Okay. So now out of 6, you can choose I of those. And then of the germinating seeds, which is 115 minus 6, which is 109, 109, you are choosing 51, let's see, 57 minus I out of those. So that becomes the probability where F itself applies. So it's a double distribution thing, where the first level of distribution has to do with how you pick the seeds. And then once you know how you pick the seeds, then it becomes a binomial distribution. So it's a lotto problem overall, and then nesting within the lotto problem is a binomial distribution.
So the result of first sigma gives you B, and the users should be in the second sigma and then you see. The result of the first distribution that you gave us. So that I has 0, and 1, and then 2, giving the value of B.
So let me double check. Let me double check the math. I is controlling the number of seeds that cannot germinate. So that means I have to fix this one to be 57 minus I, and then this is I. It will still give you the same distribution, but I need that to match this thing here. Okay. So we're quickly running out of time, but let me explain what this is. So 6 are the non-germinating seeds. 109 are the germinating seeds, of which I want this many. And then of the non-germinating seeds, I want this many. So when you add up the 2, okay, I plus 57 minus I is 57. So we always end up with 57 seeds in the attempt to germinate. We're only controlling which part of the 57 are coming from the non-germinating seeds and which part of it is coming from the germinating seeds. Is that part good? Okay. So once we have determined that we have I many of those as non-germinating seeds and 57 minus I of those as germinating seeds, then we apply the other function, which is f of dr. R is representing the number of non-germinating seeds, which is not going to contribute to the actual number of seedlings. So that's why you don't see R appearing at all within this particular function. P is representing the number of germinating seeds. That's the total number of germinating seeds for that particular way of choosing the seeds star of 115 seats. So that's why B is the upper bound and the 40 is the lower bound because we need at least 40 seedlings. Is that okay? So this one is a nesting function because you have this function here as the overarching function, and then this one here as the nested function. So for this question, I think the question specifically said, I just need the notation. I do not need the final answer because it's a double loop. It takes a little bit of time to figure that out. But to set up the structure, this is how we set it up. Is that okay? All right, so I do want to just spend one little bit of extra minute here to look at the last question. So the last question is also interesting. I can always talk about this on Wednesday, or I can record it also. I think, can I record it? I can record it, but I think having you guys to kind of be able to ask questions can also be helpful. So we can do this on Wednesday. So on Wednesday, we'll talk about the solution to the Dijkstra's algorithm homework, the A-star algorithm homework, which is now released, and also question number 4 of the exam on last semester. All right. So I'm hoping this will motivate you guys to study and actually try to think about how to prepare for the exam. Yep. Something important.
Binomial thing.
I think